Okay, we're moving right along in equilibrium chemistry. As you can see, this is going to be 7-8, 7-9, and 7-10, which I will refer to as the 7-8 lectures and assignment. So let's go ahead and see what this has to show us, some new concepts about equilibrium. All right, so you look at this question, you can see where they start to look a little intimidating, but you guys have a really good basis for this stuff right now. You know that C is concentration. You know that it's a relatively small value, so you're not going to get very many products in this reaction. Tend to lean toward that side. The temperature is one of those pieces of information that you know that's interesting, but we do not need that. It's at this temperature is when they calculated the Kc, so you don't want to be varying that because then your Kc is going to be messed up. So at any rate, a chemist tests this system and finds that we have these concentrations. And then, so this is kind of working this in reverse. Instead of plugging them in and solving for Kc, you're going to answer the question, is the system at equilibrium? If not, in which direction will it proceed? So the way to do this is to use not Kc, but Qc. And remember, that's at a moment where it might be equilibrium, might not. Most time, not so much. So you plug in those numbers and you crunch away and just solve this like we've been doing with the problems up to this point, and you get a Qc value of 15.6, no unit, and you see that Qc is greater than Kc. That means this number on the top is too big, which means we got too many products. So that's what this statement right here means. The system it's heavy on the right, and these things will compensate and get back to equilibrium by moving to the left. So given this system at these conditions Q, it will sort of right itself, if you will. So the reaction will proceed to the left until the system reaches equilibrium. And that, of course, are when those rates are the same, going backwards and forwards. But here you got too many of these guys. And even though you're not going to have that much, this is a pretty small number to say it's too many of them, but we said, Kc it doesn't favor products very often. So if you throw in some extra products back there, the system will adjust. And that's going to lead into a really important concept that we're talking about here. So a lot of times this is just done with a big arrow. I think I've mentioned this before. Sometimes you'll have a big arrow going left and a little arrow going right, because a little tiny arrow to the right is the reality. It will proceed in this direction, but at no point do these guys stop forming new SO2Cl2. It's just going faster in this direction for a time until it reaches equilibrium. All right? So these guys both will go up and this will decrease until equilibrium is established. So if you want, in your notes, put that little tiny arrow to the right, just to remind yourself that it's always a dynamic system going back and forth. So we've got some truths here about Q versus KEQ. And KEQ, remember, is the more broad term. That'll apply to KC, KP, and all the Ks that we'll be using down the road. So if Q is too big, then the reaction will proceed to the left. Is interesting political ramifications. Too many Q, it will right itself by proceeding to the left. Just a little political joke there. So if Q is less than KEQ, the reaction will proceed to the right. Okay? So Q is less than what it's supposed to be. It'll go to the right. You're light on products, and it'll increase the concentration of those products. Now, if Q is equal to KEQ, and for the purposes of this worksheet and so on, if they're close, then you say, well, it's pretty much at equilibrium. You know, if you're off by a tenth, sometimes that's just a rounding thing, and so that would be a case where they would be the same. Okay, so this is a really important concept here. And there was a French scientist named, and by the way, I was in France at a bar in the south of France talking to my French friend, and I wrote this down and I said, how do you pronounce this name? So, you're going to hear it the right way according to the true French language. So, the LE is le, and that took me a long time because he was like, le, and I was like, no, le, and then the rest of it is Châtelier. So it's Le Châtelier. That's his principal. You don't have to say the principal with the French accent. You can just say Le Châtelier, and it's his principal. And you can switch back into English. So, when a system at equilibrium is subjected to a stress, we add some products, we take away some stuff, we change the volume, we change the temperature. The system will shift in order to kind of right itself and get back, and it will relieve that stress. So we're going to talk about 3 different scenarios where Le Châtelier's principle is applied. You know, it's kind of hard to switch gears like that. So maybe we should just be an ugly American and change that into American and call it Le Chatelier. Okay? So this is Le Chatelier's principle. Or I could do the rest of the lecture in a French accent, and Le Chatelier would come trippingly from the tongue. So, if the volume of a system is, how you say, smallarized? No, decreased to make very small, then Q will go to the side with fewer moles of gas. I can't do French with all these big terms. I gotta have a script and practice it ahead of time. All right, so we're sticking with English. Le Chatelier has something to say about this. So if you got, it has to be gas, and what'll happen is if you really scrunch that volume down, which will increase the pressure, okay, so you're just pushing those things together, then the system will go to the side that has the fewer moles of gases. That just makes logical sense, because if those molecules come together, you have fewer moles of gas in there. So you force them together. And if you look over here on the left side of this reaction, there is 1 mole of nitrogen, 3 moles of hydrogen. So you got 4 moles on this side and 2 moles on this side. So this is a la Star Wars garbage compactor room. It's getting smaller and smaller and smaller. And so what happens is these gas molecules say, oh, what do we got to do? We can go either side. You want to go over here where there's 4 moles? Now remember, that's, you know, sextillions of molecules. That's a lot of molecules. So they will start to come together, and they, in essence, can cut themselves in half. Yeah, they're a bigger molecule, but gas doesn't care about that, right? That's Avogadro's rule. 22.4 liters, no matter what the gas is, right? So they'll scrunch together, and then you'll notice here that you only have 10 gaseous molecules after the pressure is applied, because the system compensated to relieve the stress. So that has to be a gas, and it has to be a change in volume, which of course pressure will do that too. So notice we on the right side here, we increase the pressure, which will decrease the volume. So then you get to how those things kind of do the switcheroo there. All right. Now, what about increasing the volume? I would say this one is not as logical, okay? Because you decrease the room, all of a sudden, oh, we got so much more room. They'll actually just go back to the more crowded side. And I don't have a good analogy for wanting to go to the more crowded side, but it is compensating for what happened when it was scrunched. It's like a spring. When you take that away, it goes back to the way it was before. So I always say with a increase in volume or decrease in pressure, it'll be the opposite of this one, where decreasing the volume, it just makes more sense. Okay, so just remember the opposite of that, it will behave in an opposite manner. Okay, so that's the stress caused from increasing the volume. So if you have this system, which is so much more relaxed and so much more space, then it'll go, oh, you know what? At equilibrium, we were over here. So you changed the gaseous molecules on both sides, and then it compensates coming back. Okay? So we're going to finish up Le Chatelier's laws. We're going to do 2 and 3 on the next video. So hang around.